Welcome. Today we shall discuss white dwarfs and Chandrasekhar's famous theory of white dwarfs. Our story begins around 1914 with a companion of Sirius. I'm sure all of you know how to identify Sirius, the faithful dog of the hunter Orion, who is chasing the bull Taurus. It had been known for quite some time that Sirius, the brightest star in the sky, has a companion. We shall call them Sirius A and the companion as Sirius B. Sirius B is much fainter than Sirius A. Now, it all began with the American astronomer Walter Adams measuring the temperature of Sirius B, spectroscopically measuring the temperature in 1914, and then its radius in 1925. Although the surface temperature of Sirius B was the same as the surface temperature of Sirius A, the luminosity of B was 10,000 times less. And since the luminosity of a star is equal to its surface area 4 pi r squared multiplied by sigma t to the power 4, where sigma is Stefan Boltzmann's constant, therefore, if the luminosity is 10,000 times less, and if the temperature is the same, it must mean that r squared must be 10,000 times smaller than Sirius A, or the radius of Sirius B must be 100 times or 1/100th of the radius of Sirius A. So the conclusion was that the radius of Sirius B is only 1/100th of the radius of Sirius A. With a mass roughly the same, the mass of Sirius B and the mass of Sirius A were roughly the same and roughly equal to the mass of the Sun. But if the radius is only comparable to the radius of the Earth, its mean density, mass divided by volume, was a staggering 1,000,000 grams per cubic centimeter. If you remember, the mean density of the Sun is just 1.4 grams per cubic centimeter, just a little more than the density of water. And here we're talking about a star whose density is 1,000,000 grams per cubic centimeter. And this rang a warning bell in Eddington's head. He asked himself the following interesting question. Are such super dense stars doomed? What did he mean by that? Stars are gaseous blobs held together by gravity. The inward pull of gravity is balanced by the pressure of radiation and by the pressure of the gas. Eddington asked himself, what will happen to the star when the nuclear reactor at its center fails? Since there is no further energy generation, the pressure supporting the core against gravity will decrease and the star will collapse. Will the star collapse to a singularity, to a point? This was Eddington's dilemma in 1925. None of the astronomers were bothered by Sirius B, but Eddington was, and rightly so. Now let us move to Cambridge University in England. Sir Ralph Fowler was a colleague of Eddington in Cambridge. Dirac, the famous Dirac, Paul Adrien Maurice Dirac, was Fowler's student at that time. In August 1926, Dirac made his great discovery concerning the statistics of electrons, which now bears his name, Fermi-Dirac statistics. Dirac gave the paper to Fowler and requested him to forward it for publication. That was in August 1926. By November 1926, barely a couple of months later, Fowler had applied these new ideas of Fermi and Dirac to save highly condensed stars such as the companion of Sirius. It is remarkable that this is in fact the very first application of the new rules of quantum physics. We are all told that quantum physics has to do with the world of atoms and molecules. Here, Fowler was applying the rules of quantum mechanics to save a star. It is only then came Sommerfeld's famous application of Fermi-Dirac statistics to electrons in metals and Pauli's application to explain the paramagnetism of metals. But Fowler's application was the very first application of Fermi-Dirac statistics. Now, what Fowler said in 1926 was the following. As the star collapsed, and it will collapse as feared by Eddington, but as its density increases, at some stage, the rules of quantum mechanics will take over from the rules of classical physics. At high densities, Fowler argued, a new pressure arises due to the combined effect of Heisenberg's uncertainty principle and Pauli's exclusion principle. This quantum pressure will arrest the collapse of the star. And thus, we will have a quantum star in which gravity is arrested by a quantum mechanical pressure. Let's try to understand this. According to Fermi-Dirac statistics, which we discussed in great detail in an earlier lecture, at the absolute zero of temperature, this is the way you populate the energy levels. In each energy level, you are allowed to put 2 electrons without violating Pauli's exclusion principle, provided their spin angular momenta are anti-parallel, till you run out of electrons, and the highest energy up to which all levels are occupied and above which all levels are empty is known as the Fermi energy, EF. Now let us consider n electrons in a volume V at absolute zero temperature, populated in various energy levels as shown on the right over here. According to Pauli's principle, as I already said, one can put only 2 electrons in each energy level. Therefore, if you populate the energy levels as shown over here, an electron gas will have an enormous amount of energy even at the absolute zero of temperature. And what more, this zero point energy will become larger and larger as the density increases. Once the quantum mechanical pressure of the electron stops the collapse, the star would have found its ultimate peace. Nothing can happen to it anymore. There is no lurking danger. What stops gravity is 0 point energy of the electrons. This energy has nothing to do with heat. It cannot be radiated away without violating Pauli's exclusion principle. Therefore, gravity has been stopped by 0 point motion. The energy of an electron at absolute zero of temperature is similar to the energy of an electron in the n equal to 1 level of a hydrogen atom. Although the electron in n equal to 1 level has an enormous amount of energy, 13.6 electron volts, it cannot spend it because there is no energy level with a lower energy. Same is true of electron gas in a dense star. Therefore, white dwarfs, if they are indeed supported by the pressure of the electron gas, white dwarfs have found their graveyard. They have found their ultimate peace. Now our story shifts from Cambridge in England to Madras, where Subrahmanyan Chandrasekhar, barely 18 years old at the time, was a second-year BSc student in Trinity College in Madras. He read about Fowler's astonishing suggestion because he had access to the journal in the university library, And he decided that let me now construct a proper theory of such condensed stars along the line suggested by Fowler, following in the footsteps of Eddington. If you remember Eddington's theory of stars, the inward pull of gravity is balanced by the combined pressure of gas and radiation. The equation of hydrostatic equilibrium read as follows: dP by dr is equal to minus gm rho by r squared, where the pressure P on the left-hand side is the sum of gas pressure and radiation pressure. The gas pressure is to be calculated according to Boyle's law, and the radiation pressure according to Stefan's law. Based on this equation of hydrostatic equilibrium, Eddington constructed a highly successful theory of the stars. Now, what Chandrasekhar decided to do was the following. He said, let me now construct a quantum star in which there is no ideal gas pressure, there is no radiation pressure, but gravity is now balanced by the pressure of the electrons, a pressure that Fowler had referred to, which arises from the combined effect of Heisenberg's uncertainty principle and Pauli's exclusion principle. Now, let me quickly recall two concepts which are relevant for us. One is the concept of Fermi momentum. At the absolute zero of temperature, all states in the Fermi sphere up to momentum Pf are occupied and all states outside are empty. We derived an expression for this Fermi momentum, and that is given over here. And the important thing is to appreciate and remind yourself that this Fermi momentum is proportional to the density of electrons to the power 1 by 3. Let me remind you once again that in this formula for the Fermi momentum, the mass of the particle does not enter. It is only Heisenberg's uncertainty principle that enters, and mass of the particle doesn't come into play there. So what we are saying is, if I compress this electron gas, then the Fermi momentum will increase. The Fermi sphere will become larger. The Fermi momentum will increase according to the formula n by v to the power 1 by 3, where n is the number of electrons and v is the volume. Then we introduce the notion of Fermi energy, which in Newtonian mechanics is simply the square of the Fermi momentum divided by twice the mass of the electron. And because the Fermi momentum is density to the power 1 by 3, the Fermi energy is proportional to density to the power 2 by 3. Please notice that unlike the Fermi momentum, in the Fermi energy formula, the mass of the particle does enter, and it comes in the denominator in Newtonian mechanics, because energy and momentum are related by the relation given here, E is equal to P squared by 2m. And as we shall soon see, this is not true for relativistic particles. But for non-relativistic particles, this is what the Fermi energy is. It is simply proportional to the square of the Fermi momentum. So as I increase the density, the Fermi momentum will increase as density to the power 1 by 3, and the Fermi energy will increase as density to the power 2 by 3. In the earlier lecture, which I devoted to a full discussion of Fermi-Dirac statistics, we derived the expression for the degeneracy pressure of an electron gas, the pressure of the electron gas at absolute zero of temperature. According to thermodynamics, the pressure is 2 by 3 into the energy density, or the internal energy divided by volume. The internal energy is the number of particles or number of electrons multiplied by the average energy of the electron. The average energy of the electron is some fraction of the Fermi energy. It happens to be 3 by 5 times the Fermi energy. Let's not worry about 3 by 5. Let us say that the average energy is the Fermi energy. 3 by 5, everything else is absorbed in this dot, dot, dot inside the bracket. Now the Fermi energy is proportional to density to the power 2 by 3. Therefore, the pressure of a Fermi gas at absolute zero will be proportional to density to the power 5 by 3, because I have to divide the internal energy by volume. So this will become n by v multiplied by n by v to the power 2 by 3 is n by v to the power 5 by 3, which is what small n is. Small n is the number density, number divided by volume. So the pressure of a Fermi gas at absolute zero of a non-relativistic Fermi gas is proportional to the number density to the power 5 by 3. So now what Chandrasekhar said was the following. Let me consider this equation of hydrostatic equilibrium. dP by dr is equal to minus gm rho over r squared, which doesn't need any modification. But instead of the pressure being the sum of Boyle's law pressure plus radiation pressure, I shall now use pressure is equal to the pressure of the electrons, which is some constant multiplied by the density to the power 5 by 3. Rho is the mass density and not the number density. Now you might ask the question, why are we not considering the pressure due to the nuclei? After all, if there are n electrons, there are also n protons, or n by 2 protons and n by 2 neutrons. They also obey Fermi-Dirac statistics. They also obey Pauli's exclusion principle. Why are we not considering the pressure of these massive particles? And the reason is that in the Fermi energy formula, mass of the particle comes in the denominator. Therefore, in the degeneracy pressure formula, the mass of the particle comes in the denominator. Therefore, if the nuclei are also degenerate, their pressure will be 2000 times less than the pressure of the electrons, although the Fermi momentum will be the same. This is because the Fermi energy will be 2000 times less. Actually, it turns out that the neutrons and protons are not even degenerate, let alone contributing to the pressure. They are not degenerate because for the nuclei, kT is still much larger than the Fermi energy. Therefore, as far as neutrons and protons are concerned, they are still classical and obey Boyle's law. But for electrons, kT is much less than the Fermi energy of the electron. This is because the mass of that comes in the denominator is 2000 times less. Therefore, although the nuclei, the neutrons and protons are still classical and obey Boyle's law, the electrons obey Fermi-Dirac statistics because they are degenerate. So Chandrasekhar proceeded to integrate this differential equation with this expression for the pressure. And let us now try to anticipate what you will get. Now let us do some scaling relations like we did when we calculated the mass-luminosity relation in Eddington's theory. To remind you once again, what are scaling relations? I'm not trying to solve this differential equation. I want to merely see how a certain quantity scales with some other quantity. So dP by dr can be approximated as P over R, where R is the radius of the star. And since the density is m divided by r cubed, the right-hand side can be approximated as m squared divided by r to the power 5. R squared is here, and density is m divided by r cubed, therefore r to the power 5. Now I can substitute for this pressure. The pressure is density to the power 5 by 3. And therefore, since density is m by r cubed, it is m to the power 5 by 3, r cubed to the power 5 by 3, which is r to the power 5. Therefore, if I use this expression for the pressure in this scaling relation over there, the left-hand side becomes m to the power 5 by 3 divided by r to the power 6. And the right-hand side, of course, is m squared divided by r to the power 5. I can simplify this, and I will find that the radius of the star will be inversely proportional to the cube root of the mass. So this is what a poor man's scaling relation will tell you should be the result if you actually integrated this differential equation with this expression for the pressure, which is what Chandrasekhar did in 1928 in Madras. And what Chandrasekhar found was this famous mass-radius relationship. The radius is indeed inversely proportional to the cube root of the mass, as we had anticipated. But then, since he actually did an honest integration, he can tell you exactly what the constant of proportionality ought to be. So, my ancient Chinese saying, one picture is worth 10,000 words. Let us plot this. This is the famous mass-radius relation for white dwarfs derived by Chandrasekhar in 1928. The paper itself was published in 1930. What is plotted on the y-axis, increasing in this direction, the radii of various white dwarfs, and what is plotted on the x-axis is masses of the white dwarfs increasing as you go from left to right. And this is the solution when you solve the differential equation. The radius is inversely proportional to the cube root of the mass. This is a very strange relation which I had referred to in an earlier picture. If you go to the market to buy some vegetable, a 1 kilogram weight will be that big, a 2 kilogram weight will be even bigger, and a 10 kilogram weight with which you will weigh rice will be even larger. Therefore, the radius of the object scales with increasing mass. Here, it scales in a reciprocal fashion. As you go to more and more massive stars, they are smaller in size. All right? Jupiter is bigger than the Earth because the mass of Jupiter is larger than the mass of the Earth. But if Jupiter were degenerate, then the story will be exactly the opposite. Now, Chandrasekhar also calculated the following two relations, which are rather important for our subsequent discussion. He calculated that the mean density of the white dwarfs will be proportional to the square of the mass. So as you go to more and more massive white dwarfs, the mean density will be larger. And the central density is 6 times the mean density. So as you go to more and more massive stars, this value of the central density will go on increasing as the square of the mass, and the proportionality constant is 6. Chandrasekhar did one more thing. From his theory and from this mass-radius relationship, he calculated what the mass of a one solar white dwarf ought to be. He found what the radius ought to be. He found that if there is a white dwarf of mass, one solar mass, then its radius will be approximately the radius of the Earth, 10,000 kilometers. At the time when Chandrasekhar wrote his paper, only 3 white dwarfs were known, and their radii had been measured. And all of them had a mass roughly equal to the mass of the Sun, and their radii was roughly 10 to the power 4 kilometers. Therefore, this theory of young Chandrasekhar was spectacularly successful in predicting the radii of the newly discovered, highly condensed white dwarfs. So the final conclusion of Chandrasekhar's theory is the stars of all mass will find their ultimate peace as quantum stars, and in their final stages they will be supported by the degeneracy pressure of the electrons. So all stars, regardless of their mass, will find equilibrium as white dwarfs. Then history was made. In July 1930, Chandrasekhar had obtained a fellowship to go and study with Ralph Fowler at Cambridge University, and he set sail from Bombay to England to go to London. During the voyage, he made a most remarkable discovery. This discovery is at the base of the present revolution in astronomy. For this discovery, 53 years later, he was awarded the Nobel Prize. By that time, he had become so famous that whether or not he had been awarded the Nobel Prize had become totally irrelevant. It took a long time for the astronomical community to absorb and appreciate the profound significance of the discovery that he made during this voyage. And I shall tell you what this discovery is. He discovered that massive white dwarfs above a critical mass will collapse under its own gravity. Let us recall what he had obtained in his theory that he calculated in Madras, that all white dwarfs will find equilibrium according to this mass-radius relationship. He had made no mathematical error in calculating this result. But he began to have some doubts about whether he had got all the physics right in this theory. This is what bothered him. He remembered that as you go to more and more massive white dwarfs, the mean density will increase as the square of the mass. And as the mean density increases, the Fermi momentum will increase as density to the power 1 by 3. Therefore, as you go to more and more massive stars, white dwarfs, the Fermi momentum will dramatically increase. And at some mass, the Fermi momentum will become comparable to m times c, where c is the speed of light, and m is the mass of the electron. And at that point, you cannot use Newtonian mechanics to describe the dynamics of the electron, because special relativity will become important. In particular, the variation of mass with velocity has to be taken into account. In what way? Let us now consider a relativistic Fermi gas in which the momentum of the particle is comparable to m times c, or the speed of the particles, v, is comparable to the speed of light. Now, as I told you, the Fermi momentum, density to the power 1 by 3, does not involve the mass of the particle. Therefore, this formula for the Fermi momentum will remain the same whether the electron is non-relativistic or relativistic. But the Fermi energy will change depending on whether the particle is non-relativistic or relativistic. In the previous discussion, we assumed that the relation between the energy and momentum is E is p squared divided by 2m, which is a Newtonian result, and it's only valid when the velocities of the particles are small compared to the speed of light. In relativity, the relation between energy and momentum is that given by Einstein, which is shown in this formula over there. E squared is m0 squared c to the power 4 plus p squared c squared, where m0 is the rest mass energy of the electron. Now, if the particles are moving very nearly at the speed of light, then the first term can be neglected in comparison to the second term, and you find this very simple result that for ultra-relativistic particles, energy is simply momentum times the speed of light. This is true for photons too. The energy of the photon is the momentum of the photon h nu by c multiplied by c, then you will get E is equal to h nu. For ultra-relativistic particles, which are moving almost at the speed of light, E and P are related not by p squared divided by 2m, but E is simply P times C. And this has an immediate consequence for the formula for the degeneracy pressure. That because the Fermi energy of an ultra-relativistic gas is not proportional to density to the power 2 by 3, but because EF is simply PF times C, the Fermi energy is also proportional only to density to the power 1 by 3. So both Fermi momentum and Fermi energy are both proportional to density to the power 1 by 3. Therefore, that's because the mass of the particle does not enter into this formula. This is as it should be, because this is what we mean by a particle being ultra-relativistic. Its kinetic energy is very much more than its rest mass energy m0c squared. It's exactly the opposite in the world we live in. Rest mass energy is much greater than any kinetic energy we encounter. Now, the degeneracy pressure of a relativistic gas is to be calculated with the formula. The pressure is 1 by 3 times the energy density and not 2 by 3 times energy density, as I had already referred to in an earlier lecture. Once again, the total energy is simply the total number of electrons multiplied by their average energy, which is approximately equal to the total number of electrons multiplied by their Fermi energy. The Fermi energy is proportional to density to the power 1 by 3. Therefore, the degeneracy pressure is energy divided by volume, which is N by V, multiplied by N by V to the power 1 by 3. Therefore, the degeneracy pressure of a relativistic electron gas is proportional to density to the power 4 by 3. Density to the power 4 by 3 and not density to the power 5 by 3. 5 by 3 came because in the non-relativistic case, the Fermi energy is proportional to density to the power 2 by 3 and not 1 by 3. And therefore, the degeneracy pressure of a relativistic electron gas, non-relativistic electron gas, is density to the power 5 by 3, but for a relativistic electron gas, is density to the power 4 by 3. Now, I've always been regarding 3 by 5, 5 by 3, 4 by 3, set it equal to 1. But in this case, you cannot, because as we shall now see, whether it is 5 by 3 or 4 by 3 is a matter of life or death for the white dwarfs. For relativistic gas, the degeneracy pressure is density to the power 4 by 3 and not 5 by 3. So, Chandrasekhar said, while he was traveling from Bombay to London by ship, he said, now, instead of integrating this equation with this expression for the pressure, which was fine for non-relativistic electrons and therefore fine for low mass white dwarfs whose density is small, and which gives this mass radius relation, he said, I shall now make the assumption that the electrons are ultra-relativistic, E is P by C, and therefore the pressure is density to the power 4 by 3, and I shall integrate this equation using this expression for the pressure. And he was able to integrate this equation exactly, mathematically exactly. And he got a most astonishing result. What he found is that a fully relativistic white dwarf, namely electrons which are moving almost at the speed of light, such a white dwarf has no radius, but it has a mass. Not only that, that mass is absolutely unique, and it is determined solely by fundamental constants. To me, along with Eddington's luminosity limit, this is one of the most beautiful formulae in all of physics. It says that if you have a star in which the pressure of the gas is due to relativistic degeneracy pressure, then that star can have this and only this mass. And that mass is determined solely by fundamental constants. hc by g to the power 3/2, 1 over square of the mass of the proton. This is exactly the same combination we found in Eddington's theory of the stars, which Chandrasekhar had isolated, and its numerical value was 29.2 times the mass of the sun. This time, It is multiplied by 0.197 and divided by the square of the mean molecular weight per electron, and that gives the famous result that this unique mass is 1.4 times the mass of the Sun. Before we dwell on this, let us see what the scaling relations say. Let us now repeat what I did a few minutes ago. This will give me P over R is of the order of m squared by r to the power 5, because rho is m divided by r cube. Now the pressure of the gas is rho to the power 4 by 3 and not 5 by 3. Therefore, it is equal to m to the power 4 by 3 divided by r to the power 4. I substitute this relation on the left-hand side over there, and I get that, and you notice that r to the power 5 cancels out. Therefore, you find that for ultra-relativistic white dwarf, we do not get a mass versus radius relationship. We only get an expression for the mass. There is no radius for the star. And of course, that mass is this unique number, 1.4 times the mass of the Sun. What is the mean molecular weight for the electron? What is the mu e squared that came in the denominator? That is extremely simple. No need to get confused about it. The pressure is mainly due to the electrons, because the neutrons and protons are not degenerate and their pressure is insignificant. But the gravity is mainly due to protons and neutrons, because the mass of the electron is negligible. Mu e is the mean molecular weight, namely the number of massive particles per electron. For the case of hydrogen atom, for one electron there is one massive particle. You leave out hydrogen. For the rest of the entire periodic table, for each electron, there are two particles in the nuclei, one neutron and one proton. Capital Z divided by capital A is 1 by 2. In other words, the total number of electrons in an atom, which is equal to the total number of protons in the nucleus, divided by the total number of particles in the nucleus, that is 1 by 2. Therefore, the mean molecular weight simply tells you that mu e times mp is the mass per electron. So if mu e is 2, that simply says for each electron, there are two proton masses that come into play when we calculate gravity in hydrostatic equilibrium, gm rho over r squared. There you have to make this adjustment. Now, except for hydrogen, mu e is equal to 2 for all the elements of the periodic table. That's because A over Z is 2. Now, this theory of Chandrasekhar, which he worked out in Madras, was Newtonian and valid for low mass white dwarfs, which are non-relativistic in the sense that the electrons are moving with speeds which are very small compared to the speed of light. But the theory worked out on the boat was for ultra-relativistic electrons. But electrons, not all electrons need to be moving with a speed almost equal to the speed of light. For special relativity to be important, it is enough if V and C are comparable. They don't have to be very nearly equal. Therefore, to calculate the energy from momentum, you really have to use the full Einstein relation that is shown over there. That he could not do on the boat, because this involved a differential equation which he had to integrate numerically. In the case where the electrons were ultra-relativistic, where E is equal to Pc, he was able to integrate the differential equation mathematically exactly. Therefore, the result he obtained on the boat was exact, even though it was extremely mystifying. But in order to calculate it without making any assumption whatsoever, please remember that this relation is true even in Newtonian mechanics. In the limit that when V is very small compared to C, this will tell you E is equal to P squared divided by 2m. Therefore, this relation is valid for all velocities. It encompasses Newtonian expression and Einstein's expression for ultra-relativistic particle. That theory, today, you could do it overnight using your most rudimentary laptop. But in 1930, Chandrasekhar had no access to computers. They hadn't been invented. He didn't have access to electrical calculator because they hadn't been invented. He didn't even have access to mechanical calculators. So he had access only to logarithm tables. So you had to integrate a differential equation using log table. But he did that. And what he found, and it took him 1 year to do that, and the paper was published in 1934 when he was a student in Cambridge University. What he found was this red curve over there. This is the exact theory where he did not make either the assumption E is P squared over 2m or the assumption E is P times C. He used the full expression E squared is m0 m squared c to the power 4 plus P squared c squared, and you get this red curve. Now, what I have plotted is a figure from his famous book. What I am plotting is the radius of the star as a function of various masses. And inside the star, so as you go to slightly more massive star, the radius becomes smaller because you're dealing with a degenerate configuration. And what he found was that a certain fraction of the star, which I have shown in red, is relativistic. So the red portion of that star is electrons are relativistic, but in the yellow region of the white dwarf, their electrons are still describable by Newtonian mechanics. If I go to a slightly more massive star, the star becomes even smaller, and the fraction of the mass which is in relativistic electrons becomes even larger, and therefore smaller in size. And finally, when it goes to the critical mass, the radius of the star goes to 0. So this was the meaning of the result that he had discovered on the board, that when the star becomes fully relativistic, the entire star from the center to the surface, electrons are ultra-relativistic, E is of the order of Pc, the radius of the star is 0. In other words, all white dwarfs more massive than this will have 0 radius. In other words, there are no equilibrium configurations where the degeneracy pressure of the relativistic electron gas can support against gravity. Such white dwarfs are doomed. And this is known now as the Chandrasekhar limiting mass, and it plays a seminal role in high-energy astrophysics. And that began to be clear only around 1972, almost 40 years after his paper. And that is why the Nobel Prize was delayed till 1983, 53 years after he published this paper. So the result that he obtained in 1930 on the boat, supplemented by an exact calculation without making any approximation either in the physics or in the mathematics, that he obtained in 1933-34, the result was that star more massive than 1.4 solar mass cannot be supported by the quantum pressure of the electrons. They will collapse. And therefore, these white dwarfs, which are supported by degeneracy pressure of the electrons, will collapse if their mass were to increase to 1.4 times the solar mass. Now, how does nature make white dwarfs? Let us go back to the lectures that I gave on the life history of stars, and in particular, try to remember what I said for the life history of low mass stars and intermediate mass stars. But first, we can ask, what is the distribution of stars as a function of their masses? What is plotted on the y-axis is number of stars with a given mass as a function of the mass. And what you find observationally is a steeply sloping power law distribution whose slope is minus 2.5. Now, therefore, there are very many more low-mass stars than massive stars. And if you remember, all low-mass stars and intermediate-mass stars end up as white dwarfs. Most of them end up as carbon white dwarf with a little admixture of oxygen. Now, if you think about it carefully, you will find that roughly 90% of all the stars that were ever formed in the history of our galaxy have already ended their lives as white dwarfs, most of them as carbon-oxygen white dwarfs. 90% of the stars. And roughly 90% of the stars which are presently shining in our galaxy will end their lives billions of years from now as white dwarfs. Therefore, the population of white dwarfs in our galaxy is truly amazing. It is an astronomical sized population. No pun intended. Astronomers have recently argued, particularly astronomers collaborating with high-powered solid-state physicists, that after billions of years, the condensed white dwarf will cool from a temperature of about 100,000 degrees to 2,000 or 3,000 Kelvin, just by radiating the fossil heat, sigma T to the power 4 times surface area. And when they cool sufficiently, they will crystallize. If the temperature of the white dwarf falls below the melting point, then the nuclei will crystallize. And it has been conjectured that they will crystallize into a diamond structure. So there is strong evidence that some of the white dwarfs which are fairly near to us, their interiors are actually solid. How do we know that? By studying the vibrations of the white dwarf. Just as by studying the vibrations of the Earth after an earthquake, you can infer the internal properties of the Earth. Similarly, by studying the vibrations of white dwarfs, which is called helioseismology, you're doing seismology, but now with stellar oscillations, you can deduce whether the interior is solid or fluid. And they have come to the conclusion that it is solid. Now, this is what is known as the thermodynamic phase diagram. What is plotted on the x-axis is the temperature in units of thousands of degrees, and what is plotted in y-axis is the pressure in units of gigapascal. Okay, very high pressure. So when you compress carbon, which comes in many allotropic forms, it can be a vapor, it can be a liquid, it can be graphite, it can be Buckminster fullerene, it can be graphene, it can also be diamond. So at very high pressure and at sufficient low temperature, carbon crystallizes to diamond forms. So the conjecture is that white dwarfs, when they cool, majority of them will become diamonds. Now, I have seen in the Smithsonian Museum in Washington the largest diamond in the world. It's about that big. Here you're talking about a piece of diamond which is 10 to the power 33 grams. And there are billions and billions and billions of white dwarfs that will ultimately end up, if this is true, as chunks of diamonds. Now let us conclude. The progenitors of white dwarf, let us recall, the progenitors of white dwarfs were low-mass stars. Stars less than 0.5 solar mass ended up as helium white dwarfs. Stars between half a solar mass and 9 solar mass, when they are on the main sequence, will end up as carbon white dwarfs with a little admixture of oxygen. They may become diamonds, but not all diamonds are forever. The title of one of James Bond movies, Diamonds Are Forever. These diamonds may not be forever. Now, this extraordinary discovery by young Chandrasekhar revolutionized our view of the heavens. People didn't appreciate it at that time. But now it is 90 years later, people realize that this is a truly revolutionary discovery. This signaled the gravitational collapse of massive stars. Soon this led to the notion of neutron stars, supernova explosions, and black holes. This great discovery marked the beginning of the era of high-energy astrophysics, which is at the base of the present revolution in astronomy. Astrophysics of neutron stars, supernovae, and black holes. It also marked, much more importantly, the end of the Aristotelian view of the universe, which I mentioned in the very first lecture of this series. Aristotle, in ancient Greece, asserted that matter of which the heavens are made is imperishable and thus not subject to generation or corruption. In contrast, the earth is made up of classical elements, earth, water, air, and fire, and is perishable. The motions in the heavens are eternal and perfect. The heavens are the realm of peace and perfection. This was the Aristotelian view of the universe that dominated astronomy for more than 2,000 years. Indeed, the serenity and permanence of the night sky was a source of security for mankind from time immemorial. So this is what Chandrasekhar wrote in his famous paper of 1932, which we discussed in detail in one of the earlier lectures. The final sentence of this paper: for all stars of mass greater than a critical mass m, the perfect gas equation of state does not break down, however high the density may become, and the matter does not become degenerate. An appeal to Fermi-Dirac statistics to avoid the central singularity cannot be made. Fermi-Dirac statistics and Pauli's exclusion principle cannot save the star from collapsing to a singularity. 1932. He went on, great progress in the analysis of stellar structure is not possible before we can answer the following fundamental question. Given an enclosure containing electrons and atomic nuclei, total charge 0, what happens if we go on compressing the material indefinitely? This question that he asked in 1932 found an answer soon after that, because a few months later, in 1932, Chadwick discovered the neutron, and that is a story that we shall pick up in the next lecture. Finally, it is necessary to emphasize one major result of the whole investigation, namely that it must be taken as well established that the life history of a star of small mass must be essentially different from the life history of a star of large mass. For a star of small mass, the natural white dwarf stage is an initial step towards complete extinction. A star of large mass, with mass greater than a certain critical mass, cannot pass into a white dwarf stage, and one is left speculating on other possibilities. And that speculation, as we shall see, was ended by Oppenheimer and his student in 1939. They will become black holes. Now, these ideas of Chandrasekhar were truly revolutionary, and they deeply upset Sir Arthur Eddington, with whom Chandrasekhar was doing all this work. In a meeting of the Royal Astronomical Society in London in 1935, immediately after young Chandrasekhar had presented his revolutionary discoveries, Eddington got up as the president of the society and said this: I do not know whether I shall escape from this meeting alive, but the point of my paper is that there is no such thing as relativistic degeneracy. Because he couldn't find anything wrong in Chandrasekhar's calculation, he attacked the very notion of relativistic degeneracy itself. He attacked quantum mechanics and Pauli's explosion principle itself. Chandrasekhar, using the relativistic formula, which has been accepted for the last 5 years, shows that a star of mass greater than a certain limit m remains a perfect gas and can never cool down. The star has to go on radiating and radiating, contracting and contracting, until I suppose it gets down to a few kilometer radius when gravity becomes strong enough to hold in the radiation and the star can at last find peace. Dr. Chandrasekhar had got this result before, but he has rubbed it in his last paper. And when discussing with him, I felt driven to the conclusion that this was almost a reductio ad absurdum of the relativistic degeneracy formula. Various accidents may intervene to save the star, but I want more protection than that. I think there should be a law of nature to prevent a star from behaving in this absurd manner. A crushing blow to young Chandrasekhar, who had just made one of the most important discoveries of the century. Both Aristotle and Eddington were wrong. The heavens are neither serene nor permanent. A star explodes every few seconds somewhere in the universe. We have already discovered nearly 3,000 neutron stars just in our own galaxy. And there are countless numbers of black holes in the universe. Aristotle's view of the universe collapsed with the discoveries by Chandrasekhar in 1930 to 34, then later discoveries by Oppenheimer and his students in 1938 and 39. In the next lecture, we shall pursue this story and discuss supernovae and neutron stars. Before I conclude, let me once again appeal to you, please do post your comments on the lectures, because that feedback is very essential for me as I prepare future lectures. Thank you very much.